So our next speaker is Anthony Kougkas from Illinois Institute of Technology, and we're switching gears here, where we'll be talking about how to leverage multi-tiered storage to accelerate I/O.
Thank you, Elena. Can you guys hear me?
Yes.
Hello. Okay, cool. So I want to start by thanking the organizers and thanking all the participants. It's great to be here. I'm Anthony Kougkas. I'm an assistant professor at Illinois Institute of Technology. And I'm thankful to have the opportunity here to introduce the effort, the joint effort between our school and the HDF group to design and develop Hermes, a distributed buffering platform. So the agenda of this talk is very short and very to the point. We're going to talk a little bit about the modern system design and the I/O bottleneck, and then I'm going to introduce the project and a little bit of technical details and the availability of the software itself. So traditionally, memory systems and storage demonstrate wildly different performance in terms of access latency and bandwidth, or even data representation. This has led to applications experiencing performance degradation due to the slow remote access to storage. Through time, there's been a lot of effort in software and different middleware libraries to bridge that gap between memory subsystems and the storage subsystems. But there's also recently a hardware answer to this problem. There's a lot of innovation in hardware where new fast flash devices and NVMe SSDs and persistent memory devices have been introduced in terms of hardware development. Those have been proposed to, in designs to be placed between memory and the slower disks, creating these multiple tiers of storage, usually organized in a hierarchy. For every little layer of these technologies, there's a lot of software, both academic and by vendors. Like for best buffers, for instance, we have DataWarp, we have DDN's IME. Most of the times, compute node, local flash devices, people just deploy and mount an ext4 or an XFS file system and they just use it locally. There are a lot of research recently for persistent memory file systems like Nova and PMFS and SplitFS. And the thing with this situation right now is that each system is independently designed and deployed and managed, and that makes very difficult to take advantage of this hierarchical storage. A lot of the times, these storage mediums with their respective software is been left to the users to deploy or mount it and use it. So this is what we've seen, and what we believe here is ideally this presence of all of those multiple tiers of storage should be transparent to applications and without having to sacrifice any I/O performance or increasing complexity of management and usage. So there's a lot of challenges associated with this deep memory and storage hierarchy. Obviously, the complexity of data movement between and among the layers of the deep memory and storage hierarchy. What do you do? Do you put some data on the NVMEs, and then how do you move them automatically to a best buffer installation? How do you make sure you use properly the API, let's say from DataWarp, to stage out data or stage in data? And a lot of those questions that increase the complexity of how scientists use this environment. And as I said earlier, each of these DMSH layers is usually independent and requires some expertise to manage. We've been talking with users at several supercomputing facilities, and honestly, there are reports that those resources have been underutilized because of the lack of maturity, in a sense of just automated software. Like the schedulers have to be updated, and those middleware libraries have to be updated to make sure that they're using efficiently each layer of the hierarchy, but also take advantage of the characteristics. Say, NVMe devices are better for random access compared to disks. So with that, we put together a great team between us at Illinois Institute of Technology, the HGF group, and the University of Illinois to work on new buffering platform or buffering system that is distributed, and its main goal would be to manage all of this complexity and abstract the low-level details from the user. This is a collaborative project, and it's funded by the NSF. Thank you, NSF, for funding us for this project. So what is Hermes, right? So Hermes is a new multi-tiered distributed buffering system. It has certain features and objectives. The first one is to manage and supervise I/O operations in this environment. Because of this environment, because of the existence of multiple tiers, we offer a selective and dynamic layer data placement, which means depending on the type of data, depending on hotness and coldness and different other priorities or hints, we can just make sure we distribute data, we place data in different tiers, so we can accelerate either your write workload or your read workload or your read after write workload and things like that. The design is very modular, very extensible, and the main objective here was performance. There are, of course, a lot of issues, fault tolerance and security and all kinds of things when you design a big distributed system like that. But our approach was to be performance oriented. We assume the environments and the supercomputing sites are relatively safe, specialized hardware, very expensive hardware. So the focus here is performance. And we wanted to make sure we can support a wide variety of applications, both scientific computing, typical stuff like Fortran and C and C++ and things like that, but also modern software stack like big data things and Apache Foundation kind of ecosystem in terms of higher level representation of data and other libraries like that. So this environment, the hierarchical environment, requires a scalable and reliable high-performance software to make sure you take advantage of all of that. In this effort, we had to develop new data placement algorithms and different memory and metadata management systems, as well as an efficient communication fabric, both within the nodes and across the nodes. As a system, Hermes is designed to be application and system aware. What does that mean? There are, during initialization, we want to understand the environment we're running on. You may have all of the layers, like I'm showing here in this picture. You may not have some of that. So we want to understand where we're running on and to make sure we take advantage of the system, as well as applications. Like if there are information about access patterns and things like that, we want to make sure we take advantage of that. The goal, of course, is to maximize productivity. We want to just let the user just do the F right, and then we take care of the rest of it, the details, where the data go, where the data land, how the data are going to be moved between the tiers, and eventually going to be flashed out of the hierarchical buffering space to the back-end parallel or distributed file system that may be present in the supercomputing facilities. We want to make sure we want to take advantage of the resources we have available and abstract all the complexity of movement and compression and things like that, while things are temporarily in our ownership. Okay, so the ecosystem itself. There's the Hermes core library. That's the main core of the whole project. The objectives here is to manage all the tiers transparently and facilitate data movement in the hierarchical space. For that, we provide a native buffering API, which I'll talk in the next slide a little bit about it. Then we developed an adapter layer where we implemented translation layers between POSIX and STDIO, MPIIO, or even publish subscribe kind of models, like the APIs from the application, so you can interact with Hermes without having to rewrite your code in your application. This just works with interception of IO calls, and then specifically mapping those structures down to the Hermes structures. And the whole effort is to boost legacy application support. Additionally to that, and since we're working with the HDF group engineers, we are developing a couple of specific to HDF5 workloads. The one is the virtual file driver. That one takes advantage of the low-level details within the HDF5 library, and mostly the splitting between what's metadata and what's raw data, and then accordingly we map those things to the hierarchy. Think an example of metadata being accessed frequently, so we place them in the RAM tier or a PMEM, a persistent memory tier, to be faster in random access and high concurrency, while we push raw data in a lower tier. Then we have also Hermes Vol, virtual object layer. That one is mostly to capture the application behavior, like it's on a higher level, so it's kind of like on the API level. Therefore, we kind of get the information about the data sets and the chunks and the hyperslabs and all of these things, and we may communicate these things down to the Hermes library to do optimizations. Again, here is simple things like driving the prefetching engine, right? So if you know what's the application calls and the patterns, you may be able to proactively elevate data from, let's say, a best buffer installation to an NVMe local to the compute node. And then we have a bunch of other smaller toolkits like the system profiler or some sort of a user schemas for custom buffering strategies and things like that. So the data model itself, we have blobs, that's the unit of data, and we went with a key value kind of approach here. The value is just an interpreted byte array, and it's stored internally as a collection of smaller buffers pre-allocated across the hierarchical space. Then we have a bucket. A bucket is a collection of blob, as it's shown here. And then we continue developing the data model, and we thought we would have some extra functionality if we could link across buckets multiple blobs. So a virtual bucket is kind of like a grouping together of things across different buckets. And because of that grouping and because of that linking together, we can attach some sort of capabilities. You could think of scenarios where you have one bucket per process, and every process is just writing to its own bucket. This way you can control a little bit the concurrency and the contention. But then again, maybe some of those blobs are representing metadata, and you want to make sure you keep those metadata in RAM. You can link all of those blobs associated with metadata into a virtual bucket, and you can attach a trait, we call it trait, that instructs Hermes to behave a certain way. Like there are traits of like ordering, like if you want to order, you keep an order between your blobs, or like group together or filter certain blobs. And we have active traits. Active traits are the ones that apply some sort of computation on top of your blobs. You could think of, hey, I want to keep this data, I'm going to buffer them in this bucket, and then I'll just attach them to this V bucket, which automatically will compress the data because that's the trait attached to that V bucket. High-level architecture here, of course, there's a bunch of components here, but the API is a simplistic kind of put and get interface, where the core is the brain of the whole Hermes is the data placement engine here that runs several algorithms about near optimal placement in a hierarchical space. There is, the buffer pool manager is the one that manages like every allocated buffer within the hierarchical space. There is a prefetcher and a buffer organizer that is background components, not interfacing with the user, but help us to do some sort of optimizations by moving around data and promoting to a higher tier or demoting to a lower tier data that leveraging hotness and coldness or priorities set from the user, these kind of things. And typically metadata stuff, there's a metadata manager that takes care of locating all the information, all the blobs placed in the hierarchy. At the end, we have a collection of network and IO clients. We can interface with RAM and NVMEs and best buffers and file systems, or even external storage. Like we can connect Hermes. The application can buffer to Hermes, and then Hermes asynchronously in a non-blocking fashion can just dump the data in a, I don't know, Amazon S3 installation or something at deployment. So in terms of the node itself, there is a dedicated core. This one is still depends on the architecture of the machine. There are multi-core machines now, and one of the cores or two, this is configurable, can be configured to be the Hermes core. This Hermes core is tasked with a lot of things in the system. Obviously, it manages the resources available to Hermes. It runs the metadata manager, some sort of messaging service, and other things. We designed it to be RDMA capable and to avoid interrupting the main CPUs from the application cores. And finally, you can think of if you have some sort of an accelerator to your node, or maybe a forwarding layer, this thing can be deployed as well on a separate set of machines. Some initial results, like the library is approaching the first public beta release this fall. And this is a typical VPIC style workload. The VPIC is a vertical particle in-cell simulation. We took, the MPIIO kernel available in many places. The Lawrence Berkeley has it, Lawrence Livermore has it. Practically what it does is just check checkpoints, the simulation results, and it's a file per process pattern. It's using HTTP files, and the logic here is to buffer the intermediate checkpoints and flush them at the end. The remote global file system in this bar here, in this case, was deployed on disks. And as you can see, the benefits are great, because in this case, we made sure that we can buffer as quickly as possible the incoming I/O. And then while the application goes back to computation, we work tier by tier, like trickling down the data all the way out of the hierarchy and into the parallel file system.